right, calculus. We are starting 5.7 optimization, and you already know I'm going to go to the notes so I get the exact phrase that was intended with these problems. So the word optimization comes from we want either a maximum or a minimum value. So what we're talking about is, let's say you're a company and you want to maximize your profit. Well, you might find an equation, and we're going to use calculus to find when that maximum would occur. And so that's why the very first suggestion given, and this is broken down, in a way that I probably wouldn't even break it down to, but at least we're starting somewhere, is you have to determine the quantity that you want to be maximized or minimized. So from there, this is optional, by the way. You don't have to draw a picture, but that could help. But at some point, you need to be able to define a variable and use some sort of formula, whether it's given to you or you find it yourself, to identify the quantities that are not valued. Typically what happens is that there will be two different equations. So that's where he says a primary equation that represents the quantity that you want to optimize, whether that's the maximum or the minimum value. Is in the same premise where I talked about maximizing profit. You might want to minimize cost, so that might be another situation. And if that primary equation contains more than one variables, you might need a second equation that involves the same variables that can help you make that relationship and be able to do that problem. And that probably makes zero sense until we get into an example, which is exactly what we're going to do. And then we can substitute. I should take a step back and talk about, earlier in this school year, we've talked about, well, how would you find the maximum? How would you find the minimum? And I'm talking about the extreme value theorem, that you want to find the derivative and find where that derivative is equal to 0 or an endpoint, because remember, the extreme value theorem could occur at an endpoint. And that way you can find that maximum or minimum value desired. Which, if I were you, I'd pause the video, copy down anything you need to, and then we are going to jump right into the examples. And it's going to take practice. You're not going to get this right away. Okay, so what we have is we are given a manufacturer with an open box. That's going to be important. A square base. Another important thing is surface area of 108. All right, so maybe we can start talking about this now. So this is my very lame open box. And the fact that it's open and we talk about the surface area means that we don't have to worry about the top of the box. A square base is saying that we have whatever side length this is has to have the same side length this way. And maybe I'll call this y because it doesn't have to be the same height. So as far as surface area goes, I'll use A for surface area. My S is, if I did surface area, my S kind of looks like a 5. We have one base is x times x, so x squared. And then we have 4 side lengths, and maybe I'll highlight, here's one of them that has an area of x times y. But there's 4 of them because, this is also x times y, this side is x times y, and then the back. And typically surface area we would have 2 of the bases, but it's an open box, so we don't have to worry about the top. Okay, so, and we also know that that area is 108, so that's worth mentioning. 108 equals x squared plus 4xy. And what we want is a maximum volume. Maybe I'll change colors and emphasize that. We want a maximum volume. So that's the primary equation. So volume, I'm assuming you would recognize that volume of a box would be length times width times height. So x squared times y. And let's see, we have way too many variables here. So it might be to our benefit. I don't know which one would be easier. See, if I solve for x squared, I would still have an x and a y there. So maybe it would be best if I took my secondary equation, subtract x squared over, and then divide everything by 4x, which would equal y. And so then I can substitute that into this problem. I hope you're okay. I feel like I just jumped into that, but I have confidence that you guys will be able to deduce after a lot of practice what the correct answer is. And what I would honestly do is cancel out one of these x's and then distribute the x over 4 in that. So I'd have 4, 108 divided by 4. Let me use a calculator. I don't know if that's that difficult of a problem, but I would end up with 27x minus 1/4 x cubed. There we go. So when we find the maximum volume, that means we need to take the derivative. So dv dx would equal 27 minus 3/4 x squared. And from the extreme value theorem, we have to set that equal to 0. And then I can solve for x, subtract or add that over. I don't know what would be easiest for you. And then I would get rid of this by dividing 3 over. So 27 divided by 3 is 9 times 4. So I'm looking at 9. That's not right. Well, I'll just write 9 times 4 is equal to x squared. So that's clearly 36. So x needs to equal 6 in order to maximize this volume. But we're still not done, because what we also need to identify is maybe we don't need all the dimensions. Well, I guess we need all the dimensions to figure out what y has to be. So what I would do is go to this equation then. I really should be color coding to figure out what y is. So 108 minus 6 squared would be 36 over 4 times 6 is 24. And I'm going to cheat and go to a calculator again. 24. I get a y value of 3. I hope all of this is making sense. So then we can go back to the volume. Oh, here it is. We wanted the dimensions. Okay, so the dimensions was a 6 inch by 6 inch. That's the square base times 3 inch, the height. And then to find the volume, it would actually be to multiply it. So 6 times 6 times 3 is, that happened to be the same thing, 108 cubic inches. I know I was all over the place on this problem. But the premise is that we're using calculus. I've seen students do this type of problem in like Algebra 1, but the difference is when you do this in Algebra 1, I've seen x and y values where students just guess and check. Like they put, well, what if x is 1? Well, then if x is 1, then you can figure out what y is, which I don't really feel like doing the math. It would be 108 minus 1 would be 107 divided by 4. So y would have to be 26.75. And then when you do that volume, 1 times 1 times 26.75, you get 26.75. And that volume's not very large. So then you move on to the next value, next value, next value. And then eventually you get to the correct value, so 6. And typically what students do is they continue on. Like try 7, they try 8. And what calculus does, it takes the guesswork out of that method. And you get an answer right away. Well, I shouldn't say right away, because it does take a lot of practice. So as I move on to the next problem, we have a box is built from a rectangular piece of cardboard. So it might be worthwhile to draw that picture of a rectangular piece of cardboard. 25 centimeters, I'll write that up here, by 40 centimeters. looks like we're cutting a square from each corner and then bending. Okay, so I'm reading this as a square from each corner. And in order to make it a box, I think all of these corner pieces have to be exactly the same. Call them X, 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 X. And then bending those pieces up, so it would form a box. Find the size of the corner square which will produce a container that will hold the most amount of soup. Ugh, I don't know if I want soup out of a cardboard, but anyway. So we're talking about volume. How do we find volume? Well, length times width times height. I'll write that down first. And you have to use your imagination for a second, because the length in this, maybe I'll change colors. This length would be represented by 25 minus, well, there's an x on this side and an x on this side, so it would be minus 2x. And same thing with the width. It would be 40 minus 2x. Now think about this critically, because as you fold this piece up, then the height of the box would just be x. There you go. I think we can work with this. I would simplify, because I don't really want to do the chain rule, product rule, or anything like that. So maybe foiling that out, 25 times 40 would give me 1,000. Let's see, that would be minus 50x minus 80x. 50 and 80 would be 130. If I was smart, I would have done something else, but that's okay. My something else would have been distributing at the same time. So 1,000x minus 130x squared plus 4x cubed. And now I feel like we could just do the derivative. So dv dx would equal 1,000 minus 260x plus 12x squared. Set that equal to 0. I think I'm just going to go to a calculator at this point, because I've already been using a calculator. Maybe I'll just share with you mine. Go to y equals, and if you're afraid that you're going to type this in incorrectly, you could probably type it in the way the original one was. Maybe I'll do that. 40 minus, oh whoops, forgot my 2 in there. Times x. And honestly, I don't even care about that equation. What I care about is the derivative. I'm going to make my, because it only makes sense to have a window of x values, and it'd be impossible to have an x value larger than, well, even 12.5 would be too much, because you can't cut into the side of the piece of paper. You know what I mean? I guess what I'm talking about is if x is bigger than 12.5, you'd have nothing. So I'll just guess 12 and hit zoom 0. And it looks like that's where we're going to get our exact answers. So that must have been factorable. Second, calculate, just to confirm that it's an integer. Because if you look at it, it looks like it's exactly 5. Yeah, x equals 5. So this must have been factorable, but I got lazy. That x must equal 5. So find the size of the corner, which must be cut to maximize that volume. And for the sake of what the factors are, I'm going to pull up the answer key. So, oh, he actually goes through a little bit of work to show increasing to decreasing on that previous problem. Okay, so that's how you would have factored. And he does a little bit of work, I'm just out of time, to prove why it was a maximum and why this one would have been a minimum. And he drew his picture a little bit differently, but that's okay. So if you want to pause the video and copy down his work, which is a little bit better than mine, that is fine with me. And I'll see you in the next video to continue this lesson.